Greetings from Brussels, Belgium, and welcome to this second installment of what now appears might actually be a series of lectures on programming. If you will remember, last time I gave you but a glimpse of what programming might actually look like. Today, however, I will endeavor to illustrate programming as a practical problem-solving skill. In particular, I will teach you two methods of solving a rather ubiquitous class of problems that we all tackle on a daily basis. Before I get down to that, I will first make a short review of what we did last time, using a framework that distinguishes the features of a language into primitive elements, which I've mentioned two: primitive data like numbers, integers, and decimal fractions. But what I haven't mentioned is that irrational numbers like pi or e or imaginary numbers like I are not allowed in C++. We will later see why. Then we've seen things that are not numbers, like strings. For example, the string hello. And we've also seen operators, primitive operators. Like the arithmetic operators, addition, subtraction, multiplication, and division. And also we've seen a rather strange kind of operators that did input and output from the standard input and standard output, like the extraction operator and the insertion operator. And then we've seen how to combine these things into sentences. And we call this means of combination. The first mean of combination that I introduced were expressions. And these expressions looked very much like the ones you learned in school. For example, we combined numbers with arithmetic operators to derive an expression like this. And then an expression can also be grouped and built into a bigger expression by using additional operators and additional primitive data. However, expressions are not the smallest standalone parts of a valid C++ program. If you'll remember, those were statements. And statements were basically expressions terminated by a special symbol. And this symbol is the semicolon. And now, with statements, we could build programs. And the way we compose statements is by sequencing them. So another mean of combination was sequencing. And it was just laying out expressions from top to the bottom. For example, like this. Or this. But the important thing is that with sequencing, we introduced the notion of time in the text of our programs. So when we evaluated a program, we had to pay attention to the order, because it's not the same if we flip these two statements, the output. Well, in this case, it will not be a problem, but in general, it is an important thing. And finally, we've seen one mean of abstraction. And what means of abstraction basically are methods of introducing new names, new nouns, if you will, to the language. So with this, we had the power of introducing variables that had certain values bound to them, like this. And in addition to all of this, we've also seen objects. Things that we didn't really elaborate upon. And these objects were Cin, which stood for standard input, Cout, which stood for standard output, and variables like this, like the variable A or variable B or whatever. And finally, we've seen functions. Well, we've just seen one specific and particular function that is called main. And in whose body all of our programs were placed in. With this said, we can now go to the first new topic of today's lecture. And I'll motivate this with the following piece of text. And at the same time, I will introduce a new way of making variables that are now available because the language changed in the meantime from the publishing of the first video. So now we have a different C++ than we had before. And what this enables us is to introduce variables in the following way. So I'm introducing a variable A and I'm binding it to a value 4. Instead of doing it like this. And there's a reason why this is better. But for the purposes of this lecture, the only reason is that it makes things simpler and less ambiguous. And now, once we have this variable, let's print its value to the standard output, which we've seen in the last lecture how to do. And this piece of text is something that we can evaluate using our mechanical model. The way we did this is that we made some space for the standard output and some space for the memory wherein all the variables were stored. The execution of a program began with the first statement. And in this case, the first statement is double A4. So what this means is that we define in the memory a variable called A that has associated with it a box, a place to store values. And this says to bind the value 4 to the variable A. And this finishes the first statement. Now the second statement is a complex statement. It has several parts to it. And as before, we proceed from left to right when we evaluate expressions of this kind. So first, we evaluate this expression. This expression evaluates to the value of what's stored in the box associated with the variable A. And then we send this value, the number 4, to standard output. Having done that, we need to evaluate this part. And what this part does is it tells us to proceed to the next line of output here. And this is nothing new. However, if I do this and introduce a new piece of language, we have a problem, because now there is a new expression of the type we haven't seen before. So let's look at it in more detail. A equals 5. This is what computer scientists call an assignment expression. It has three distinguished parts. The equality symbol, which is the assignment operator. And this assignment operator has things on its left and right side. So we will distinguish these sides as left hand side and right hand side. Because assignment expressions are a crucial part of the language, I will be very careful and mechanical in explaining the way we evaluate them. So I'll write down precisely the steps that lead to the evaluation of such expressions. The first step in evaluating an assignment expression is to evaluate right hand side. Let's call this the order of evaluation. Once we've evaluated the right hand side, we evaluate the left hand side. Then we assign value of the right hand side to the value of left hand side. And finally, we return as the value of the expression, the value of the right hand side. Because if you remember, every expression has to have a value. That's the only meaning of an expression. And now we will evaluate this expression here using these 4 steps. So the first step says evaluate the right hand side. The right hand side is a literal, a number 5. So the first step, number 5, because it's a literal, it evaluates to itself. So the value is 5. In the second step, we need to evaluate the left hand side. On the left hand side, we have a variable. Variables evaluate to the boxes associated with them. So the variable A will evaluate to the box that contains the number 4. The third step tells us to assign the value of right hand side, the number 5, to the value of the left hand side, which is this box. Assigning is equivalent to overriding the contents of a box. So what happens now in the third step is that the box that contains the number 4 now becomes a box that contains the number 5. And we can replicate this effect on our memory as well while we are evaluating this expression. So we will overwrite the contents of the variable 4 of the variable a with the number 5. Finally, as the last step of evaluation, we have to return the value of the expression the number 5, because that's the value on the right hand side. Just write return 5. So this, if we take a look at this, after evaluation, we will have a slightly simpler expression. It looks like this. And we know how to evaluate this. So what happens is that the number 5 gets printed or sent to standard output, and we proceed to the next line. However, there are certain peculiarities with this particular expression, and to really reinforce the idea of these steps of execution, we will evaluate this expression. With the contents of the variable a being the number 5. So the first step is to evaluate the right-hand side of the expression. But the strange thing in C++ is that variables don't have the same values on the right-hand side and the left-hand side of expressions. So the value of the variable a on the right-hand side is just the number stored in the box. So a plus 1 evaluates to 5 plus 1, that's the value stored in the box, and this evaluates to 6. Whereas in the second step, where we need to evaluate the left-hand side of the expression, the value of the variable a will be a different thing, as we've seen. It will be a box. So the a will evaluate to a box containing as its value the number 5. This is important to have in mind when we evaluate expressions like this. Finally, we will assign to this box the value of right-hand side. That's the number 6. And we can replicate this effect on our memory as well. So the value of the variable a now becomes 6. And finally, we return as the value of the expression this number, the value of the right-hand side. So if we were to write this, what would appear on standard output is number 6, and we would proceed to the next line of output. So in C++, the equality symbol does not stand for equality as we know it in mathematics. It's a different kind of beast. It's assignment. So for any mathematician, this does not make sense. And in C++, as we now see it, it does. And this idiom is something that will often appear in the text of our programs. So just to explain what kind of values can appear on the left-hand side of the assignment operator, I will give you an example of an illegal expression. Five equals 3, that is, assign the value 3 to 5. This is not valid because on the left hand side we can only have variables. We need, or to be slightly more precise, a box. We need to have a box that we can assign a value to, and literals do not have any boxes associated with them. With that said, I do have to point out that in C++ it is rather rare to write assignment expressions. What is much more common is to write assignment statements. So what you would normally see instead of this is first assigning a value to the variable a, and then printing it out. Adding a semicolon symbol to an assignment expression results in an assignment statement. And assignment statements can be combined like any other statements, that is, sequenced. However, assignment expressions give us the power of a different combination. Because the assignment operator, like any other operator, can be used to build more complex expressions. So, for example, I could do the following. Introduce a variable b, bind it to a value 1. Or, for example, let's not bind it to any value. Let's just say this. And the result of this is that b has a box associated to it with a singular value. We don't know what this value is. And then I will introduce variable c in the following way. And what we have now is a compound assignment expression. Let's evaluate this. If you remember the rules of evaluation, the first rule was to evaluate the right-hand side of the expression. And the right-hand side of the expression is this. So the right-hand side is an assignment expression. Then we evaluate the right-hand side of this expression, assign it to the variable b, which has the effect of writing the number 2 in the box associated with b, which again simplifies because the expression b equals 2 results in a value, and that value is the number assigned to b. This expression gets simplified to the following expression, which has the effect of writing the value that is the number 2 to c. Before we can do this, we need to introduce c, associate a box with it, and then write the number 2 as its content. And this is actually very similar to how these expressions work. Let me show you. If we were to evaluate the statement or the expression cout hello endl, what we would do is proceed in a slightly different order, like this. So we first evaluate the left-hand side, which has the effect of sending hello, the string hello, to standard output. By performing hidden assignment, by changing cout, which is something like a variable, and simplifying this expression to the following. And then we send endl, or assign it, to our object cout, which represents standard output, which has the effect of proceeding to the next line. Finally, this simplifies into the very object cout. But normally, we're only interested into this effect that happens during evaluation. So we discard this value by putting a semicolon at the end of the expression. This effect is something that we called, or computer scientists called, side effects. We've seen it with assignment in the third step. In addition, for the assignment expression, we have the effect of a value being assigned to a variable. So up till now, all expressions were only evaluating two values, but with the introduction of the assignment expression, we have the additional effect, or the side effect, that changes variables. And this is a crucial part of the language, and that's why these statements predominate C++ programs, because what statements actually say is that we're not really interested in the value of the expression preceding the semicolon, but rather the effect of this expression. Can we take a break? No. Let's take a break now. Alright, now that you have operational knowledge of assignment, I will introduce you to a really powerful feature of the language. And to motivate this, we will generate lyrics of a typical modern song that goes something like this. As it's obvious, the lyrics are quite repetitive, and we'll limit ourselves to generating only the first 5 verses. One way to do this, with the knowledge you have, is to write out 5 statements that do printing out to standard output. However, as all true programmers, we are lazy and we don't want to do this. What we will do instead is describe a process that repeatedly executes the same action. And in C++, there is a special means of combination to do this, or in other words, a special form. And this special form is known as a for loop. So I will now first write how we can describe such a process, and then I will explain the particulars in the syntax. So we begin by writing for, the name of the loop. Then I introduce a loop variable, I, set it to 0. I write loop condition and a loop increment. And now I specify the action to repeat, which is one verse of the lyrics. Right here, right now. This for loop has three distinguished parts. Let's give them names so that we can discuss them. The first part is this, and it is called loop initialization. The second part is this, and we will call it loop condition. Finally, the third part is something that we call loop increment. Because this is a special form, there are special rules to evaluate it. The best way to understand a piece of text in C++ is to evaluate it. And that's what I'm going to do now. And by observing my evaluation, you will have understood the meaning behind this special form. The way we execute this special form is in steps. And to do this, I'll have need of memory and also a place to send stuff out. That is our standard output. The first step in evaluating a for loop is loop initialization. It's this statement here. What it instructs us is to introduce a variable called I and bind it to the value 0. This variable is also known as loop variable. Having performed this step, the loop initialization step, we will not perform it again. It's only executed once at the very beginning of the for loop execution. The next step that will be performed in each iteration of the loop is the loop condition. And it's this expression here. And it instructs us to check whether the value of the variable I is less than 5. The value of the variable I is 0, which is obviously less than 5. So if this check passes, then we are allowed to execute the body of the for loop. And the body of the for loop is this statement here. So the body is made up of only a single statement. And this statement is something that we know how to execute. So we just print out the string right here. Right now. And we proceed to the next line. Having executed the body of the loop, we need to execute the loop increment. The loop increment is this thing here, which we've not encountered before. Plus plus I is an expression that is equivalent to I equals I plus 1. And this we know how to execute. The operator plus plus is known as the increment operator. And it's just a shorthand for writing this expression. It saves us a character. So once we once we've executed this statement, we need to execute the loop increment. And the effect of that is that the variable I is incremented by 1. So its value is now the number 1. And we can return here. The loop initialization is no longer performed. So the only thing we do is check the loop condition. Whether the value of the loop variable is less than 5. It obviously is, so we are allowed again to execute the body of the for loop. So let's do it. Right here, right now. Having executed the body of the for loop, we again perform the loop increment. And the effect of that is that the variable I now becomes 2. We again check the loop condition. It holds, 2 is less than 5. So we may again print out or execute the body of the loop. We perform the loop increment. The variable I becomes free. We check the loop condition. 3 is still less than 5. So we are allowed again to execute the body. And we proceed to the next line. Again, we perform the loop increment. I now has the value 4. We check the loop condition. It still holds. So we perform the body again. Right here, right now. And proceed to the next line. We execute the loop increment again. The value of I is 5. And then we check the loop condition. Is the value of the loop variable less than 5? Is 5 less than 5? Well, the answer is no. It is not. And it is at this step that the execution of the for loop is terminated. Once the loop condition no longer holds. And the next thing that happens is that execution proceeds from the first statement after the for loop. In this case, there are no statements in the for loop. So the meaning of this for loop was to repeat the body, the statement, cout right here, right now, endl, 5 times. Another way we could have expressed this idea is to have initialized the loop variable to 1 and change the loop condition into I less than equal 5. I will let you convince yourself that this is equivalent. What I'm really interested now is into examining the sort of expression we have here. Because this is something we've not seen before. So let's zoom in. I less than equal 5 is a new kind of expression by the name of relational expression. The interesting thing about these expressions is that they evaluate only to 2 values. So the only possible results of this expression is either falsehood or truth. It could either be false or true. And these 2 values are also commonly known as Boolean values, attributed to a famous British mathematician, George Boole, that invented the so-called Boolean algebra built on top of these 2 values. And we'll see more of them in the next lecture. For now, let's just develop a more profound understanding of these relational expressions. The key part of our relational expression is a relational operator. In C++, we have all the common relational operators we've already encountered in mathematics, but let's just enumerate them. we have less than, we have greater than, we have less than equal, greater than equal, and we have equality, which is expressed with double equal signs, and we have difference. So let's see how they operate, just to reaffirm what we already know. The expression 3 less than 4 evaluates the true. The expression 3 less than equal 4 evaluates true. The expression 3 different than 4 evaluates true. The expression 3 different than 3 evaluates the false. Applying relational operators to variables is only slightly more complicated. So if we had variables double a equal 4, double b equal 3, I could write this: b less than a. And in this case, the variables will just evaluate to the values stored in the boxes associated to them. So this will transform into 3 less than 4, and we've already seen, or we know, this is true. And it's the same for all other cases. Like, for example, is a different than a? It's not. It's false. Finally, let's take a look at equality. Equality in C++ is expressed by double equality symbols, because the equality, the single equality symbol, is reserved for assignment. So you could, for example, write this. And this expression will evaluate the true. With variables, it works very similar to this case. If I were to write a equal a, this will evaluate the true. The way this operates is that we transform variables into values contained in their boxes. Because, for example, if I were to change b, and well, let's leave it like this, and let's introduce a new variable, double c equal 4. And if I were to say, is a equal to c? The way equality operates in C++ is only on values of variables. So we don't really test for identity, because c, if we were to introduce it, it would have a different box than a. So they're not the same thing, but we're only concerned with their values. So in this case, the expression is also true, because the value of a is 4 and the value of c is 4. However, as I already illustrated in multiple occasions, C++ is not quite like mathematics. So for example, we cannot write this. In C++. It would result with a type error. Now let's illustrate why this is erroneous. We have a compound expression, so we evaluate the first sub-expression. 3 less than 4, this evaluates to true. So we can substitute this expression by the following more simple one. Is true less than 5. But this now is a type error. We cannot compare truth or falsehood with numbers. They are simply not comparable. And there is a different way of expressing this in C++, and I will show you slightly later at the very end of the lecture. Okay, so now you have an understanding of how a for loop operates. You've seen relational expressions. So I guess it's about time to showcase usefulness of for loops. So for example, let's express the process of printing out the first 5 natural numbers. Just to remember, the first 5 natural numbers are 0, 1, 2, 3, and 4. And we want them to appear on standard output. The way we could do this is to iterate the loop variable from the first natural number to the 5th. So I'll just modify this for loop here. And I will express this idea. I want to iterate my for loop, my loop variable from 0 to 4. So I'll write like this, I less than 5. And I will increment the loop variable by 1 at each step. And in each step, I will print out the value of this loop variable. And this program, or just this special form, expresses this very idea. And let's convince ourselves that this is the case by evaluating the special form. So the first step is to initialize, or to perform the loop initialization step, where we introduce the loop variable and set it to 0. We check the condition, it's true, and we execute the body of the loop, which has the effect of sending to standard output the current value of the loop variable, that's 0. And we proceed to the next line. Execute the loop increment step. I becomes 1. We check the condition holds, and then we again execute the body of the loop. So now in standard output we have the number 1. And this process will repeat. And we will have this sequence appearing on standard output. At this step, when we printed out the number 4, the value of the loop variable I has to be 4. And that's the value that was just printed out. The next step is to execute the loop increment. So we change I to 5. And we check the loop condition. 5 is no longer less than 5 is not less than 5. So the execution of this loop is terminated. And the result is exactly what we wanted. The first 5 natural numbers in ascending order. What if we would like to print out the first 5 natural numbers in descending order? So instead of this sequence, what if we want to produce this sequence? One way to do this is to iterate the loop variable from the number 4 to the number 0. So instead of initializing I to 4 or to 0, we will initialize it to 4. And then we need to change the loop condition into this. So while the loop variable is greater than or equal to 0, the loop will continue. And now at each step, we cannot increment the loop variable. We need to decrement it. And for this, there is an analogous operation, or operator, minus minus. So minus minus is a decrement operator. And minus minus I, as you might expect, is equivalent to I equals I minus 1. So let's see if this thing works. We initialize the loop variable I to the value of 4. Check the condition. 4 is greater than or equal to 0. We execute the body. Decrement the loop variable I. Check the condition. It's still valid. Execute the body. 3. Decrement the loop variable 2. Check the condition. Valid. Execute the body. Decrement the variable. Check the condition. Valid. Execute the body. Decrement the variable. Check the condition. It's still valid. 0. Decrement the variable. Minus 1. Check the condition. No longer valid. Loop terminated. And the result is exactly what we wanted. How about generating the first 5 square numbers? Just to remind you, the first 5 square numbers would be 1, 4, 9, 16, and 25. The way we obtain them, as we all know, is by multiplying the number by itself. So it will be very elaborate, just so that we can understand the idea behind writing the for loop that will produce this sequence. So the second is generated by 2 times 2, the third by 3 times 3, the fourth by 4 times 4, and the fifth by 5 times 5. What we see here is a pattern. Values that change from one sequence to the other by 1. So what we could do is represent these values by our loop variable that will iterate from 1 to 5. And then at each step, we would evaluate this expression. Because the loop variable will now iterate through all of these values. So let's express this. We want our loop variable to range from 1 to 5. So we write I less than equal 5. And we want it to iterate in steps of 1. So we write I++. And as the body of the loop, we will print out the value of this expression. Let's change this. And we have expressed the idea for generating the first 5 square numbers. Let's just confirm that this works. I want to be very mechanical so that there's no chance of misunderstanding. The first step, loop initialization. We introduce I and bind it to 1. Check the condition, less than equal to 5, true. Execute the body. We evaluate the expression, it evaluates to 1. So in standard output, we put 1 and proceed to the next line. Increment I, 2, check the condition, true, evaluate expression, 2 times 2 is 4, and print out 4. And this iterates, so the next number is 9, next number is 16. And finally, at the last step, we have I equals 5. Evaluating the expression in the body generates 25. Incrementing the loop variable results in I having the value of 6. And the condition no longer is valid. So the loop execution is terminated. And the result is the first 5 square numbers on standard output. So we can do many interesting things by using or abusing these loop variables. A very similar idea to this one is to print out the first 5 multiples of the number 3. For example, such multiples would be 3, 6, 9, 12, and 15. And the way they are generated is by the following way. So 3 times 3 is 9, 4 times 3 is 12, and 5 times 3 is 15. So this is the way we would generate the first 5 multiples of the number 3. Again, we notice a pattern. We have a sequence of values that we can generate by our loop variable iterating from 1 to 5. So this expression could be rewritten like this. And the only thing we need to change in the text here to generate the first 5 multiples of the number 3 is this. Oh, very simple. But still hard if you've never thought about it this way. So in general, it's always a good idea to really think about the problem. Our problem was generating the first 5 multiples of the number 3, so we really took a deeper insight how we generate these multiples. And then we noticed a pattern, and this pattern gave us an idea to use the variable I to generate such a pattern. And it's only through experience that you can gain such creativity. But very soon it will become a process that you will not even think about. It will just become one of the idioms you will use in programming. And with this, I believe that you now have a pretty good understanding of how a for loop works. So the next step would be to introduce a method for solving a very common problem. And that problem is the sum of a sequence of numbers. So we have a sequence of numbers 4, 2, 8, 3, 11, and we want to calculate their sum. This is something we know, we learned in school. But the way we learned in school was by observing the teacher performing a process. To express this process in C++, we need to be very elaborate. And since we're only starting to learn how to program, I will express this process in a very detailed and mechanical way. And such expressions of processes are also known as algorithms. So today you will learn your first algorithm. I will not really go into the details of what an algorithm is. You will understand just by observation, and you will have a very good operational understanding of what algorithm is. The first algorithm that solves this problem is called the adder algorithm. And it has 3 steps. So to compute the sum of a sequence of numbers, we first introduce a variable sum and set sum to 0. As the second step of this algorithm, for each element or number, since we only have numbers, of the sequence, do this. Sum equals sum plus number. And finally, once we've exhausted the whole sequence, the result is now stored in sum. A simple algorithm, but extremely useful. Let's express this algorithm in C++. We will introduce a variable sum. And set it to 0. That's the first step. Then, in the second step, we have to loop for each number of the sequence. That's a for loop. So for, and let's generate the sequence by producing it on the standard, input. So on our standard input, there are 5 numbers. They may be the same: 4, 2, 8, 3, and 11. So we have a loop for 5 times. We introduce the loop variable, set it to 0. We loop for 5 times. We now understand this. And at each step, we perform this. Sum equal to sum, sum equal to sum plus number. However, there's a problem here. We don't know what this number is. Our values are on standard input, so we will have to extract them from the standard input and place them in this auxiliary variable number. And we know how to do this. So we'll introduce a variable variable number. We will not bind it to any value. And then at each step, we will extract it from the standard input and store it in the variable number. And then we will add it to the variable sum. And this expresses our second step. The first step says that the result is now stored in sum, so we can print it out. You can print out the value of the variable sum. And this here is the C++ incarnation of the adder algorithm. Let's convince ourselves that it works. I'll make our memory here. Our standard input is here. And our standard output may be here. First step introduces the variable sum and binds it to 0. In the next step, we have to evaluate the special form, for. We know this. So we introduce the loop variable I, bind it to 0. We check the condition. It is satisfied. 0 is less than 5. Then we may execute the body of the loop. The body of the loop instructs us to introduce a variable number, which is bound to a singular value. So we don't really know what the value is. We haven't specified. Then we extract one value from standard input and store it in the variable number. So we extract the first value, that's the number 4, and we store it in the variable number. Then we perform this assignment statement. Sum equal to sum plus number. So we add this value. In this step, that's the number 4, to sum. We assign it. So at this step, the value of the variable sum is 4. We execute the loop increment step. I becomes 1. We check the condition is valid. But one other thing, you need to be very careful here. Once we exit the body of the loop, so this here is the body of the loop, everything between the curly braces, all the variables that are introduced in the body disappear, they die. And then, once we re-enter the body of the loop, we have to reintroduce the variable number. As this is repetitive, I will no longer erase the number, the variable number, but the real meaning of the body is this. So all the variables have to be removed. Sometimes it can be a problem. And so the value is not bound. We extract another number. That's the number 2. We store it here. And then we evaluate this expression, sum plus number. The value of sum is now 4. So we add this to 2, the result is 6. And the result of sum becomes 6. We increment I to 2. We extract another value, 8. We add this to sum. So the value is 14. We increment I. We check the condition, it's valid. We extract another number. So number is now 3. We add this to sum. Sum is now 17. We increment I. Check the condition, valid. Extract another value from standard input. Store it in number. Add this to sum. Increment I. Check condition. Condition no longer valid. Loop terminate. Once the loop is terminated, we have to remove all the variables that are introduced in the body and in the header or in the initialization part of the loop. So we remove number and we remove I. The last thing to do is to execute this statement here. And this statement sends the value of the variable sum to standard output, and that value is the number 28. So, by being very elaborate, you should now have a pretty good understanding of how and why this algorithm works correctly. And it's a very useful algorithm. So let's play a little bit with it. We've seen how to generate a sequence of squares and multiples. How about calculating a sum of the first 5 odd numbers? Let's give that a look. What are the first 5 odd numbers? This is the number 1, the number 3, the number 5, the number 7, and the number 9. How could we generate them? Well, one way would be to start with the first number I, with the first number, that's 1, and then at each step increment by 2. So we can do this by using a loop variable I in the following way. So we will begin iterating with the first odd number, that's the number 1. We will loop till the 5th odd number, that's the number 9. And at each step, we will no longer step by 1, but rather by 2. And this can be written like this. Okay, but there is a shorthand for expressions of this kind. Instead of writing it the long way, you can write it shorter, like this, I plus equal to. Or this would be equivalent to sum plus equal number. And this thing here is again a new operator, which has the same name as the plus plus. It's another increment operator. And we'll be making use of this operator as well, as it does save some space, that is characters. So let's return to our for loop here. We've just expressed the way to generate the sequence of odd numbers. The remaining thing to do is to compute their sum. So what I can do is just say sum equal to sum plus I. Like this. Or, as I've introduced the new operator, sum plus equal I. And this will calculate the sum of the first 5 odd numbers. That's one way to do it, by producing these numbers in this iterative way. We can also maybe think in a slightly different way and say that the first odd number is actually the first even number minus 1. And the second odd number is the second even number minus 1. And the same for the rest. And then we can generate this sequence like this. Where I iterates from 1 to 5. And this way, make it more clear that we're actually repeating this loop for 5 times. Because when we observe this text here, it's not immediately obvious that this will repeat for 5 times. So we will make it obvious by rewriting in this way, by using this insight. So I will now iterate from 1 to 5, and it will increment by 1 at each step. And instead of incremented by I, which would produce the sum of first 5 numbers, not natural, we will write this expression, 2 times I minus 1, which will have the same effect as the stuff we wrote before. So as you see, we can be very creative and play around, and it's really the case that there's like an infinite way of expressing the process of generating the sum of the first 5 odd numbers. And now that we're actually talking about the sum of the odd numbers, it might be interesting to show a mathematical identity that was known in the ancient world. So a long time ago, in the age of yore, there lived a powerful wizard whose name was Pythagoras. And this powerful wizard was also extremely good at mathematics. And he invented a way of displaying numbers by pebbles. And then he would arrange these pebbles into very curious shapes. So for example, the way he would represent the number 1 would be with 1 pebble. The number 4 with 4 pebbles. The number 9 with 9 pebbles. And he would arrange them in square shapes. And these are known as square numbers, which are a type of so-called figurate numbers. And these square numbers are the same square numbers we know, because if we arrange pebbles in these shapes, we will produce a sequence of squares. But the interesting thing here is there are different kinds of figurate numbers. For example, we can use numbers that have this shape. And they are called mnemonic numbers. The interesting thing about these mnemonic numbers is that they appear in square numbers. So we can see them here. You can see the first mnemonic number here, the 1 pebble. You can see the second mnemonic number here. It's this figurate number here. And we can see the third one here. And what this means is that any square number can be expressed as a sum of odd numbers. Because these numbers, this is the number 1, the number 4, the number 9, and this is the number 1, 3, and 5. So the number 5, by implication, can be expressed as 5 plus 3 plus 1. It's a very curious geometric identity or geometric proof of this mathematical identity, that the sum of a sequence of odd numbers generates squares. So as your homework, I would like you to compute or to generate a sequence of square numbers without using multiplication, just by using addition and relying on this identity. It should not be very hard. You already know how to generate odd numbers. Okay, now that we've really elaborated upon the adder algorithm, let's take a look at a slightly different problem that will again require a new feature of the language to be introduced. Let's take the following problem. On standard input, there are 5 values, and I will enumerate them. 5 minus 1, 4 minus 8, and 12. The problem is to compute the sum of the numbers from standard input, but only those that are positive. So in this case, we're only concerned with number 5, 4, and 12. What we know so far is how to iterate through the 5 numbers on standard input and how to compute their sum. But in this case, we need somehow to not include these numbers. So let's start out by what we know. We're again implementing the adder algorithm. We will iterate for 5 times. And at each step, we will read a number from standard input. And now comes the tricky part. We need to select only those numbers that satisfy a condition, and that condition is them being positive. In C++, this is performed by conditional execution, and there is a special form for this. It's called the if form, and I'll just write down this idea. So if the number we just read is positive, which means that it's greater than 0, or yeah, let's keep it like that. Only in this case shall we perform the summation. And we will close the body of the loop and print out the value in sum. So this text here expresses the solution in C++ for a process that will compute the sum of those numbers from the standard input that are positive. The thing that I introduced here is a special form called if that performs conditional execution. It has one important part, and it's this condition here, which we will more commonly call a predicate, like condition or predicate. And predicates are expressions that evaluate to true or false. So far we've seen relational expressions as one type of such, as one type that satisfies the predicate concept. Let's execute this for loop to see how this works. It's not really surprising, but still we want to be very elaborate. So I will introduce again memory. We introduce variable sum, bind it to 0, introduce loop variable, bind it to 0. We check the condition holds. We introduce the variable number. We read a number from standard input, store it here, and then we perform conditional execution. The way this is done is that we first verify whether the condition holds. Is the number greater than 0? It is. In this case, we can execute the action of this conditional statement. And the action is this body here. So we perform this statement, which tells to add 5 to the current value of sum. So the value of sum is now 5. We increment the loop variable. Its value is now 1. We check the condition of the loop. It holds. So we can again read a number from standard input. I'll just remove these so that we know where we are. So the next number is -1. We store it here. And we again perform conditional execution. Is the number greater than 0? No, it's not. In this case, we don't perform the action. So we just jump into another iteration, which means that we read another number from standard input, number 4. And in this case, the condition holds. 4 is greater than 0, so we may add it to the sum, which is 9. We perform another iteration. I is now free, the loop condition still holds. We read another number, -8. We perform conditional execution. -8 is not positive, so in this case we don't increment the sum. We jump into another iteration. 4 is still less than 5. We read another number from standard input, that's the number 12. We perform conditional execution. 12 is positive, so we can add this to our current value stored in the variable sum. So the result is now 21. We perform loop increment. The value of the loop variable is now 5, and the loop condition is no longer satisfied, so the execution of the loop is terminated. And with this, we have calculated the sum of those numbers on standard input that are positive, thanks to this new feature of the language that enables conditional execution. Let's examine a slightly different problem, which is very simple. If we have conditional execution, there is one number on standard input, and we need to write a program that will print out a message stating that the number is positive or negative, and this statement has to be truthful, so should not lie. Let's pick one number, 1, so it's positive, and our program could be written in this way. We begin with the main function. We will introduce a variable number to store the value from standard input. We will read this value. And then we will perform conditional execution. If this number is positive, let's in this case agree that 0 is also positive, we will print out the message. Number is positive. However, the number can also be negative. In this case, we would have to write another conditional execution. So if the number is negative, we print out the message number is negative. However, this predicate here already answers the question whether the number is positive or negative. There is no reason to retest again for negative numbers. And C++ allows us to be more efficient, so as not to perform needless predicates twice. So if this predicate is true, the number is positive. If it's false, then we could do something on this value as well, because there are two outcomes to a predicate. In this case, C++ allows us to write, instead of this, else, and then execute this statement. So if the predicate evaluates to true, we evaluate the action of the special form if. If it evaluates to false, we evaluate the alternative. And that's the semantics behind the if-else special form. We will now take a short break, and then we will return again and examine what else we can do with predicates and conditional execution. Alright, we have a new problem to solve, and that problem states that there are 10 numbers on standard input, and we need to send to standard output the sum of those that are single digit. And this we will solve in a rather elegant way, and in the same time show you how to resolve this issue we had before with the notation. So in mathematics, a single digit number would be a number that satisfies this predicate. As I explained before, we cannot write this in C++. Now I will show you how we can resolve this little problem. But first I'll just write the whole thing and then explain the detail once we get to it. So we have 10 numbers on standard input. We're again performing the adder algorithm that we've seen. So we introduce sum, bind to 0, loop 10 times. And then, in each step of the loop, we evaluate a predicate equivalent to this one. And we do it in C++ like this. Sorry, but first we need a number. So I will read a number. And then we test. So this number has to be greater than 0, and it has to be smaller than 10. So that's the way we express it in C++. This here, this digraph, is called the logical AND operator. The symbol that composes it is known as the ampersand, and it used to be part of the English alphabet. So when they were reciting the alphabet, this would appear as the last thing, and they would say as n per se n, and when you do this very fast, it contracts into ampersand, so it's known as ampersand. And the whole thing again is a predicate. That is an expression that evaluates only to two values, either to true or false. And if this predicate holds, then we want to do our adder thing. So in this case, when the number is single digit, greater than 0 and smaller than 10, we will perform the step of the adder algorithm and add the number from standard input to sum. And that's the body of the loop that needs to be repeated 10 times. And we can also close the curly brace from the main function. This operator is curious in the sense that it operates only on Boolean values, that is, on values that are true or false. So on its left-hand side and on its right-hand side, it has to have expressions evaluating either to true or false. And it will only be, the whole expression will only be true if both of these sub-expressions are true. And we can also express this as a table. So if this is the value of the left-hand side, and this the value of the right-hand side, this expression, so L and R, we read this just as and, behave as follows. So if both of them are true, this is true. If either is false, it is false. And if both are false, it's false. So it's a very easy thing to remember. What if we change the problem and instead of computing the sum of single-digit numbers, we want to compute the sum of those that are not single-digit? Well, in C++ there is an easy way to do this by using an operator known as the negation operator or the not operator. The not operator is a unary operator. It operates only on a single expression. So the table for the not operator would be, let's call this expression, and this the application of the operator on expression. If the expression is true, when we apply the not operator, it will be false. And if the expression is false, after application, it will be true. So it just inverts truth value. And returning to the problem here, a number is not single digit, and we can express this like this. So if the number is not single digit, then we compute the sum. And you can try out this yourself. So I believe I repeated it sufficiently so that you can do it on your own and convince yourself that this will actually work. Although I could still talk more about these logical operators, I will refrain from doing it now and leave it for later. Because what I want to do now is introduce a new algorithm to show you how to solve another interesting problem. And that problem is finding the minimal value in a sequence of numbers. So both of these problems that I'm illustrating are things you know. And it's for a reason, because it's much easier to understand mechanical procedures that we already know how to perform. So we're just learning how to express them. And later on, we will tackle with ideas that you probably have never heard. And by then, you will not have trouble reasoning in this algorithmic manner. So, our problem is the following one. On standard input, there are numbers. Let's again limit ourselves to 5 numbers. 8, 2, -1, 4, and 12. What we want to do is to send to standard output the smallest number in this sequence. Again, I will express the algorithm in steps. So it has several steps. The first step is to set the variable minimum to first value of the sequence. The second step is for each number in sequence, if it's less than minimum, so if number less than minimum, minimum will become this number. And once we've exhausted the list, result can be found in min. Okay, so let's just translate this into C++, which you could probably already do yourselves now. So we have a distinguished variable called minimum. But it has to be set to the first value of the sequence. We obviously need this value, so we will introduce an auxiliary variable, double num, and read one value from standard input. And then, as the first step says, we will assign the value of this number to minimum. Having done this, we can proceed to the second step. So we have to loop across the remaining numbers. In this case, it will be across 4 numbers. Double I 0, I less than 4 times. And then we perform conditional execution. If the number that we read from standard input is smaller than the value stored in the variable minimum, we perform this. So minimum becomes this value now. And that's all we do in the loop. Finally, we print out the result. Let's convince ourselves that this actually does what it should do. We have numbers on standard input. Let's introduce memory and standard output. First statement, introduce number num, variable num. Bind it to a singular value, read a number from standard input, or extract it, store it in the variable num. Then introduce variable minimum and assign to it, or yeah, let's make this really clear that we're not doing assignment. That's the reason why I didn't want to use the notation from the first video. Let's bind it to the value of the variable num, which is 8. And then we need to iterate 4 times across all of the numbers from standard input. So we will abstract now the for loop. We understand that we need to perform 4 iterations. First step, read the number from standard input. Store it into num. Check whether num is smaller than minimum. It is. We perform conditional execution. Assign num to minimum. So minimum now becomes 2. We read the next number, -1, and store it to num. Is -1 smaller than 2? It is. So we assign this value as the new minimum. So -1 is our new current minimum. We extract another number, 4. Is 4 smaller than -1? It's not. So we don't do anything. Finally, we extract the last number, 12. And again, we check is 12 smaller than -1? It's not. So at the end, we execute the final statement and we send the value -1 to standard output. So this algorithm obviously works for this sequence and this problem. And now that we know how to find a minimum value in a sequence, it's actually very easy to find maximal value in a sequence of numbers. So the only thing we need to do is just rename this all occurrences of minimum into max. And then change this predicate. Now, if the number is greater than max, our new maximum becomes this number. Isn't this great? As this video is quite a bit long, I will not do any more problems using this algorithm, but I will give you a homework assignment. And what I want you to do is to take a sequence of numbers, for example, to have 10 numbers on the standard input, and to find the second smallest number in the sequence. Not the first, but the second. It might be a little challenging, as you'll realize once you start solving it. But still, it's much more easier than finding the first smallest one. So if you're really, really looking for a challenge, try to find the first smallest one. Later on, in some of the subsequent lectures, I will show you a very easy way to do this. But for now, yeah, you'll have to do it the hard way. But just using the knowledge I gave. And with this, I will conclude my lecture. I will give you a mental teaser for the end. And kind of illustrate or help you better understand what sort of things algorithms are, by showing you an algorithm that cannot be expressed in C++. But it's easy to perform if you have a ruler and a compass. this algorithm is something that ancient Greeks knew. And it's very simple. Probably all of you know how to do it. So the problem is, we have a circle. We know the center of the circle, and we have a point, P. And the problem is to construct a tangent on this circle. So a tangent is a line passing through P and intersecting the circle in one point that we call T. And the way we solve this problem is by using an algorithm. So the way the ancient Greeks would do it, construct this tangent. They would first draw a line between these two lines. Then they would use a compass like this, from this line, from this point to this point, to find the symmetry. Then they would produce a line between these 2 points, which halves this length BC. And then from here, from this point H, they will use a compass like this. And they will generate 2 tangent points. So it's a very simple algorithm, and yet it cannot be expressed in C++, for the simple reason that lines and circles are not entities we can express in C++, nor do we have any means of using a ruler and a compass. So the algorithm that we will be discussing about in the subsequent lectures will only be a subset, not a small subset, but still a subset of all the possible algorithms that a human computer, if you will, can perform. In this lecture, you've seen what serious programming might actually look like. In the process, I've introduced quite a few new language features, and I've also shown you 2 algorithms for solving a common subclass of problems. Composition into subproblems is a very powerful problem-solving technique, and I will continue to elaborate on it in the subsequent lectures by introducing additional new algorithms for solving these small problems. So that once you're confronted with a problem, you will know how to recognize patterns. And for each this pattern or subproblem, you will have a solution. So the only creative process on your part will be to assemble solutions to these subproblems into a final solution. And this will carry us a long way until at some point in the distant future, I confront you with problems that will no longer be decomposable into disjunct subproblems. And at that point, only sheer creative power will lead you to a valid solution. But by that time, you will have become quite an accomplished programmer. At this point, I'd like to thank you for your attention, and I'm looking forward to seeing you next time. Bye-bye.